Well, welcome everybody to Hydroterra's latest webinar. Today our topic is Optimising Dewatering, Improving Water and Wastewater Management with Advanced Water Balance Strategies and Innovative Technologies. Seems to be a very popular topic. We've got over 360 registrants, so fantastic to have you all here. Our presenter today is David Harris. He's the founder and director of a consultancy called HydroView Consulting, which is based in Sydney. Before we commence, I would like to begin by acknowledging that we conduct our work across this great land, and for that privilege, we would like to thank the traditional owners. Hydroterra respectfully acknowledges the Boon Wurrung people of the Kulin Nation, where we are located today, and we pay our respects to their elders, past and present. There's a picture of our presenter. A little bit about our presenter. So David is a seasoned hydrogeologist. And water management specialist with over 14 years experience in environmental consulting. With a strong academic foundation in applied hydrogeology and geology, he has built a rounded career delivering high-quality technical advice on groundwater, surface water, and environmental contamination across a range of market sectors. David's expertise extends across many elements of the water cycle, with extensive experience in groundwater and surface water investigations, water balance assessments, integrated water management plans, water treatment and discharge impact assessments. Recently, his technical leadership has supported major construction projects including the M6, M8, Sydney Metro tunnelling packages, WestConnex and Western Sydney Airport, where he has developed monitoring and management plans, construction water management strategies, conceptual and numerical models, and trigger action response plans. His recent work has also included development and technical review of water balance assessments for quarries, mine sites, and industrial facilities. David is a certified environmental practitioner and director of HydroView Consulting, a specialist water advisory consultancy based in Sydney, New South Wales. He is a committee member of the International Association of Hydrogeologists, New South Wales chapter, and a communications officer for IAH in Australia. In his spare time, David enjoys the trials of gardening and some home hydroponics. Just a little bit more about our friend David. He studied originally geology in Plymouth in the UK, and then did a Masters of Hydrogeology in Newcastle, also in the UK. How did he end up out here? Well, in 2010, he came to Australia working with RPS. He left us for a little while and then came back again in 2016, working with SLR and a range of other Tier 1 consultants. This year, David's taken the leap of faith to set up his specialised consultancy, HydroView. As most of you are probably aware, we love your questions and really welcome questions during the presentation. We will read out those questions at the end of the session. To log a question, please use the Q&A button at the top of your screen, and we will follow up with that. Why does Hydroterra do these webinars? Well, we like to share knowledge, we like to facilitate education, and we like to take an industry leadership position by understanding what the industry needs. All right, so without further ado, I'll hand over to you, David. Thanks very much.
Thanks, Richard, and thanks to everyone for dialing into this presentation today. I'd like to start by talking a bit about my experience in this field. So as Richard's mentioned, I've been a practicing hydrogeologist for close to 15 years now, specializing in water quality and site water management. I picked up a growing interest over the recent years in dewatering management strategies, and in particular in wastewater management in relation to dewatering and water discharges. Fundamentally, water balance is a central component of managing water effectively when it comes to dewatering options for recycling, reuse, or discharge of water to the receiving environment. The topics I'll cover today speak to the theme of water balance and water management, with an emphasis on wastewater management components. I'll discuss at a very high level the fundamentals of water balance and why they matter, including a brief history lesson. The nature of planning and approvals for dewatering and discharge, which shares similar but not exact architecture across the various states in Australia. I'll discuss monitoring and environmental compliance with a focus on approvals and compliance for the reuse and discharge of water, and explore typical dewatering and discharge management systems that I've encountered through my experience. In the latter parts of the talk, I'll take you through several case studies based in New South Wales in which water balance and sustainable water management has been essential to operation of the project. So without further ado, let's move on to the beginning. So the concept of water balance has early roots, where major civilizations such as the Romans, Egyptians, Indus, and Chinese flourished by integrating water balance into their day-to-day lives. In each of these early civilizations, water balance management was essential for things like managing crops, providing drinking water, managing urban drainage, and mitigating flood risks. Fast forward then a few thousand years to modern history, and things take a drastic change at the onset of the Industrial Revolution. At this time, there was a major gear shift in the demand for water as mass production required ever-increasing volumes for industries such as textile mills, iron and steel mills, steam power generation, and industrial-scale mining operations. To meet these escalating demands, engineers developed a wide range of invasive systems to store, transfer, and supply water, including high-capacity pump and pipe networks, extensive sewerage systems, and expansive reservoirs. The shift from this limited-scale social uses of water to consumption by mass production not only increased the stress on water resources, but resulted in widespread water pollution, which had profound impacts on aquatic ecosystems and human health. Rivers and streams that were once sources of drinking water and sustenance often became open sewers, with manufacturers discharging vast quantities of untreated waste directly into waterways where it mixed with equally copious amounts of raw public sewage. In Sydney, a long-lasting legacy of this industrial impact can still be traced in the sediments of Alexandra Canal, which, when disturbed, can still cause major water quality impacts in the lower Cooks River. By the 1980s, it was widely recognized in Australia that there was a need to protect water resources. The cumulative impacts of poor management practices, coupled with harsh realities of Australia's variable climate, led to a series of economic and environmental crises. The crises forced a reassessment of how water was valued, managed, allocated, which prompted a series of significant reforms aimed at recognizing environmentally and socially sustainable limits for water use and embracing the principles of water balance. The Council of Australian Governments Water Reform Framework was a key turning point in how Australia managed its water resources. With some of these key principles enshrining in this reform were allocations of water to the environment, the establishment of water sharing agreements, and the separation of water property rights from land title. The COAG water reform was also formally recognized the National Water Quality Management Strategy, or NWQMS, which today forms the basis for sustainable use of water, community values, water quality guidelines, and integrated planning for water resources. And although it's important to note, although the reform was implemented at the national level, it was adopted by each state as a blueprint for a consistent approach to sustainable water management. Each state then drafted specific legislation and withheld the responsibility for sustainable management of their water resources through water access licenses, licensing take, and protecting water quality through pollution control, and discharge licensing. In New South Wales, water sharing agreements and water access licenses are managed through the Water Management Act, and pollution control and discharge licensing are managed through the POEO Act. So aside from important changes to legislation, there was further engineering and scientific effort needed to formalize methods for assessing, modeling, measuring, and monitoring water resources. Between 1965 and 1974, slightly preceding Australia's water reform, there was a global recognition to form and a formal effort to advance and standardize hydrological methods, which until then were varied and non-standard. Themes included recognizing the need for global data comparability, developing guidelines for measuring environmental parameters such as stream flow, groundwater, evaporation, rainfall, and water quality. The IHD also saw widespread promotion of the concept of the hydrological cycle, which we'll all be familiar with from high school geography, and formal integration of the water balance equation into a range of hydrological methods. Now, since its integration and standardization, the water balance equation has formed the foundation of further advancements in water balance modeling into increasingly complex applications, where increasing numbers of complex variables must be accounted for. And in this slide, you can see how an increasing number of components that are used to balance water requires an increasingly complex equation to balance flow. At its simplest level, the water balance needs only to account for rainfall, runoff, infiltration, and evaporation. At its most complex level, we see the need for accounting for interbasin transfers, storage, processed water use, groundwater inflow, and seepages, which are not untypical for more complex mine sites where you might have multiple pits, for example. So the starting point for any water balance is to prepare a conceptual model. This is, in essence, a simplified representation of a real-world system. At this stage, we're defining the system and its boundaries, the time period over which the water balance will be assessed. We're identifying the system components that relate to inflows, outflows, and storage, and describing the interactions between these components. Once the components have been determined and compiled, the next step, typically adopted, is to prepare a visual representation in the form of a conceptual diagram. That might be a three-dimensional diagram, a cross-section, or it might even be a process flow diagram. For a mine site, this might be a diagram showing groundwater inflows, dewatering paths, discharge routes, storages, evaporation ponds. For a water treatment plant, this might comprise stormwater and groundwater inflows, wastewater inflows, storage, land application, and then discharge to the environment. It's important at this stage, the conceptual stage, to identify any data gaps so that they can be addressed if needed through further investigations and data collection. For example, determining groundwater inflow rates might require some seepage monitoring or permeability testing of aquifers. For discharges, it might be necessary to collect further information on flow conditions and water quality in the receiving waterway. A lack of information in this regard can cause propagation of error down the line where you end up with the wrong results. For irrigation to land, it may be necessary to collect information on soil types and soil hydrology to determine if there's suitable structure and buffering capacity of that soil to accept water. In any way, once the conceptual model has been formed, the next step is to identify the level of complexity of the system and decide on which method water balances are going to be assessed.
Dave, I've got a question for you. So things like estimating groundwater inflows to proposed tunnels and that sort of thing have some fairly large uncertainties around them. When you're doing these sort of works, and there's obviously uncertainties across other estimates as well according to the water balance, is there some sort of criteria you set for what's an acceptable level of uncertainty, and do you report that?
Yeah, absolutely. So there are guidelines that speak to uncertainty modeling and uncertainty analysis, and they're specific to different applications when it comes to water balance. For groundwater modeling in particular, uncertainty analysis is becoming quite a common aspect where we're asked to assess the variables and their individual certainty into a cumulative certainty. So, for example, if if you have a large domain with only a few monitoring points and permeability tests, your uncertainty might be quite high, and you might need to go and put in new groundwater wells to monitor not only water levels, but to conduct permeability tests and really understand your hydraulic permeability.
All right. Move to the next slide.
I think we're still on that one. Sorry, Richard. Yeah,
Oh,
there's a bit
sorry.
more. Apologies. So look, for most simple systems and discrete areas, analytical spreadsheet model-based tools can be used. And in fact, spreadsheet models are widely used because of their accessibility, their flexibility, and the familiarity of most users with using spreadsheet tools. This structure typically involves setting up a ledger of inflows, outflows, and storage components over discrete time steps, such as days, weeks, months, or years, and then using those built-in spreadsheet functions and user-defined formulas to calculate each component of the water balance equation. One shortcoming of using these spreadsheets is that it can be prone to formula errors, incorrect cell references, hidden mistakes. They're also quite limited use when it comes to handling large data sets and complex time-varying processes such as feedback loops and probabilistic analysis. So in situations where these factors are significant and the user might choose to adopt a numerical software package, which is often accompanied with a graphical user interface to make the process user-friendly. Otherwise, you're going into coding and writing code and trying to work through that, which not a lot of people do. There are, I'd say, a limited range of numerical predictive software packages on the open market. And one of the problems with these is they all require payment of a license fee to use, and those license fees do not come cheaply. GoldSim for example, is widely used and accepted in the industry as a robust integrated water balance model with a range of applications. And I would say from my experience is particularly common in mining operations. One of the drawbacks of GoldSim, however, is it doesn't have a physically based groundwater flow engine like ModFlow or FeeFlow, and it typically represents groundwater inflows into excavations using quite simplified approaches that might not reflect reality. When it comes to groundwater and dewatering, ModFlow is the industry standard. So it's a widely used computer code. It solves the groundwater flow equation. The visualization and analysis is provided through a range of both commercial and open source GUIs, which run the ModFlow code. And the ModFlow code itself is also open source, so you can use that free of charge. Or if you want an easier user interface, you can pay for a commercial package. In New South Wales, if we look at now surface water and rainfall modeling, music is widely used for simulating urban stormwater systems. Now, its primary purpose is actually in design. It's to help urban stormwater professionals design and evaluate the performance of various stormwater management strategies, which are often related to water-sensitive urban design. It tracks the movement and storage of water within a modeled system through different components. And finally, the last item there in our flow diagram, the model for effluent disposal using land irrigation is largely used in Queensland to simulate and assess the long-term sustainability and environmental impact of wastewater irrigation schemes. This software is great because it replaces the commonly used spreadsheet-based models that every other state will use. I don't, from my experience, I haven't seen any other software packages that model this wastewater irrigation. And it's a process-based model. It works through daily time steps, and it simulates complex interactions between effluent sources, irrigation, climate, soil characteristics, and crops.
Getting back to your comment about GoldSim there versus ModFlow, you seem to be thinking that a physically based model like ModFlow is going to be producing better data than, I guess, what's more a black box GoldSim style model. In reality, do you see that? Like how much of a variance do you get? Like, I know it's a lot of effort to build like a ModFlow model, but often I find there's not enough clarity in the different parameters that are going into that physically based model to really get that additional value. What's your view on that?
That's right, and it's completely dependent on your operation and the sensitivity of those different elements to how they affect water balance. For a dewatering operation where groundwater is your principal concern, a ModFlow model using the ModFlow code is going to be your go-to source. Whereas if you've got more of a coupled groundwater, surface water, process water system that needs that integrated modeling, you might be better off going with something like GoldSim. in any case where it's something, you might want to consider risk as well. For example, if you've got a risk of subsidence that you really need to assess in great detail, or a risk of drawdown that might affect groundwater dependent ecosystems, you'd be better going with a mod flow model that can accurately simulate groundwater recharge and drawdown using those finite element methods.
Just before we move on, so in terms of, you've mentioned some sort of regulatory stuff previously. Are there guidance documents between states that actually specify which modelling approach you should be using, or are they leaving it up to sort of professional discretion?
It's typically up to professional discretion, but that being said, in the when it comes to then the approvals pathway, the regulators will have a definition on what they require then to gain approvals. And so for mine sites, if you were to come in and say we built a gold sim model, the regulator might turn around and say it's insufficient for X number of reasons, so we'd want you to go with the gold sim model. There are guidelines out there at the national level and some at state level on the methods to be adopted for groundwater for modeling, and especially for groundwater model, there's the Australian guidelines on groundwater modeling. So that's what I'd refer to there when considering your modeling approach, at least with ModFlow.
Okay, thanks for that.
Awesome. So now there's an important adage in the field of hydrological modeling, which states that if you put garbage in, then you get garbage out. And that's to say, if your model is based on inaccurate or incomplete data, then you may find the outcome doesn't represent reality, and you're going to have to go back to the start when you realize that. So in order to build a reliable model, we must have reliable data, and that data that is data on the necessary inputs for a water balance analysis. The first place to start on your journey is to gather data at your computer. So don't go charging out into the field. Compile that data, that what you already have and what's available and reliable from the public domain. The most common variables that I see for dewatering and discharge projects are climate data such as rainfall, evaporation and evapotranspiration, groundwater levels, aquifer hydraulic properties, stream flow data, water quality data, and your pumping rates. For more complex dewatering projects, you may require information on things like your process water demands, your water reuse volumes, your different surface land uses for land application schemes. Like say, for example, you want to go and irrigate a field. What is the soil over there? What is the crop type? What is its crop efficiency and irrigate, evapotranspiration rates? And does the soil have enough permeability for you to safely irrigate that area? Regardless of what you need, the place to start is at your desk. Build the conceptual model.
You don't want to talk to any more of those specifics?
I think, sorry. Yeah, I think next slide for now, Richard.
Okay.
Yeah. So once you've gathered your desktop data and you've built the foundation of your conceptual model, it might be time to start collecting the field data and fill in the critical data gaps that you found from your desktop study. And that might be only a few things. It might be a lot of things. In any case, you really need to understand what your data gaps are before you go out in the field. Like the desktop data, you want to make sure that you're collecting and compiling information that's relevant to your specific application. So don't go out and test for everything. Go and target those objectives to what it is you're doing. You wouldn't, for example, go and collect field data on soil permeability if you weren't intending some sort of land application for managing water. Once you have a clear idea of what you need to collect, it's time to go and plan out a suitable strategy for collecting that data. And there's a wide range of both standard and innovative methods which you can adopt when collecting field data relevant to water balance and dewatering discharge assessments. The method you adopt will depend on a combination of site-specific factors and the quality and type of information that you need. For example, you may want to determine the variability of flow in an ephemeral creek and the corresponding water quality during a rainfall flow event. In this instance, standard methods might include the use of a weir coupled with a water level sensor and a rising stage sampler, or an automated water quality sonde. Some of the newer methods might include image-based velocimetry, or microwave Dopplers coupled with nutrient electrochemical sensors or passive samplers. Whatever you do, whenever collecting your field data, it's important to consistently consider the objectives. and whether or not your field data collection is of sufficient quality and quantity to address those objectives. And for example, regulatory authorities may require that you have at least 18 to 24 months of water quality data and flow monitoring for a receiving environment to adequately characterize the baseline conditions before you start a project which could impact on flows and water quality. Or in another example, you might be required to gather information on the seasonal variability of water levels in a mine void and to determine whether or not there's a suitable available storage for transfers from other pits during part of the mine extension program. For many of the projects, especially dewatering discharge projects, it's critical to have a strong understanding of the baseline conditions before the project commences, and wherever possible, to maintain monitoring at those same locations throughout the project lifecycle. This gives you a modicum of consistency anyway that you can refer back to when it comes through to that impact assessments and your compliance. The monitoring forms foundation not only for planning and approvals, as I say, but later on for licensing and compliance.
From your experience, which ones of those parameters are the ones that trip us up most? Which ones are the hardest to get?
You know, we've always had problems with ephemeral flow monitoring and collection of samples in ephemeral creeks. You know, taking something that's reliable and representative of an ephemeral creek over a season or several seasons, it needs you to install, ideally these automated samplers that capture the water quality throughout the rising limb, the peak, and then the falling limb of that unit hydrograph, for example. Once you've got several of those examples of different unit hydrographs for different magnitude of flow events, and you've coupled it with your water quality, you can get a better idea of the natural flow variability before you commence a project. But it takes, it's a cost, and it's a highly technical thing. So I would say that is something that, when it's done right, it can really help you out. But a few times it's done to that level of detail that's needed.
We often get involved monitoring like groundwater surface water interaction projects. It's a tricky area to predict, isn't it? So just sort of is that something that you look at on every project? Is that part of your conceptual model, or?
So the variability or the unpredictability, is that right?
That's right. So I don't know. Say it's the Yarra River in Melbourne and its connection to the CityLink tunnel during its early phase of work. Is that something that you would
Yep,
logically
absolutely.
expect to need to do?
It's part of the uncertainty analysis, and it's part of that uncertainty assessment. And the best we can do with that is come up with statistical derivations to give best fits on what we expect average and reasonable worst case conditions or best case conditions might be. So we take a sample and we say, this is our sample. We'll run the statistics on that and hope that it's representative of the population. So that's the best we can do. We're always getting snippets of information in environmental monitoring. It's very rare that we have comprehensive continuous data, that's reliable and can be used universally. And part of that is, I think, it comes at a cumulative level where, a project starts and ends and they collect data for a short period of time and then it just disappears into the ether. My personal view is if there's a way, and I think a lot of people hold this view, is that, all that data that people are out capturing and collecting on these systems, if it was collected and centralized into, an open source area, I think there'd be a lot of benefits to, and a lot of advancements in environmental management. But unfortunately, a lot of that is locked behind private and confidential or, locked doors. So.
Yeah, and I think it always will be.
I don't think it's ever going to change. I don't think it can change, unfortunately, but you can always dream.
Yeah. Let's move to the next one.
Yeah. Grant, so now we've talked a bit about the technical. It's time to talk a bit more about technical, but that is planning, approvals, and compliance. And it's important to note here that not all projects will follow the same process or require the same level of detail. Small-scale, low-impact projects may only require a few of these steps, whereas a large-scale project may require all of them to a great deal of detail. What I'll talk about here is what can be expected for some of the larger projects, and to give you an idea of broad considerations in the approach for planning, approvals, and compliance process. To start with, it's important to consider the application of the water balance, as I've discussed already. It's often not a one-time exercise, but rather it's an evolving process and a tool that will provide critical insights through the entire life cycle of a project, from its initial conception through to the end of its operation. For dewatering discharge projects, the process typically starts with identifying the need for discharge, conducting initial site investigations, characterizations, risk assessments, which are then fed into a water management plan. This might be a single plan or a master plan with a series of sub-plans governing the sources, transfers, storages, uses, and discharge of water. The impact assessments and the management plans are then submitted to a regulatory authority and stakeholders to obtain approvals and licensing necessary for the project to progress. So for a dewatering project, it may be necessary to obtain water access licenses and works approvals to take the water. Or for stressed catchments, there may be a need to acquire water access through trading markets to effectively buy an allocation from another access license holder, as none are currently available and the system is over capacity. To then discharge that water, it might be necessary to engage further with a different regulatory authority and stakeholders again to obtain a permit to discharge or a discharge license. And typically, the EPA is the regulatory authority for any discharge permits where the water quality does not comply with the National Water Quality Management Strategy, ANZG, default guideline values. And you'll recall we discussed the NWQMS earlier in the history. The ANZG guidelines were born out of that NWQMS. So in New South Wales, and I'll speak to my knowledge, it's an offence under Section 120 of the POAO Act to cause water pollution, with water pollution being defined quite broadly as anything that changes the physical, chemical, or biological properties of a water body, including artificial and natural water bodies. So it even applies to stormwater drains. You can't go and pollute a stormwater drain, chiefly because it's a waterway, but also because it will then discharge into receiving environment. There's often a misconception that an EPL is not required for discharges if the project is not a scheduled activity. And the response I have to this is that an EPL is there as your defense against breaches of Section 120 of the POAO Act. And if your discharge causes water pollution, then you could be charged with a contravention offence, unless you have an EPL in place for your level of contamination. Often for larger projects, the decision might be made to commission a water treatment plant to treat that water quality prior to discharge. And while it might not be possible to achieve the ANZG guidelines, these water treatment plants can reduce the potential for water quality impacts to levels that are acceptable for the regulatory authorities. In New South Wales, a test of this is whether there's a risk of significant harm to receiving waters. And I've had the pleasure of writing a number of discharge impact assessments for water treatment plants to support the licensing of their discharges. I would say one of the common themes in this licensing process is the need to demonstrate that all reasonable and feasible options have been explored before there is a need to discharge water. So reusing and recycling water for other purposes would serve the benefit of minimizing the volume of water that's discharged to receiving waterways, and it can significantly mitigate those risks. And that's what the EPA is trying to do. They're trying to mitigate the risks to receiving waterways by exploring all other options that are reasonable and feasible. And that consideration of reasonable and feasible falls under Section 45 of the PO Act, where they have to consider the economic viability in their licensing functions. So my advice to the larger sites is, wherever it's possible, try and explore the feasibility of achieving a zero discharge site or a closed loop system. Throughout the planning and approvals and compliance, it will be necessary to maintain a consistent monitoring program to demonstrate that you're minimizing potential risks to the environment. So for temporary or construction projects, this will help determine that your project's not causing material harm to the environment and it's complying with your license conditions. For longer term projects, you might need to continue monitoring for an extended period and have regular reviews of that monitoring program as the project evolves.
If I was a developer, say, and wanting to do one of these enormous projects, the upfront exercise before I get any certainty on the project being approved or not versus having some comfort, right? I'm just curious to know
Yeah.
um, if the poor old developer is starting over at the start phase, how much of this
Mm,
has to be done before they've got any level of certainty that the thing's going to
yeah.
proceed?
Like there's always a great deal of risk, and characterizing that adequately earlier and getting all your experts in early on in I would say the design phase and the pre-feasibility phase is where you need to do a lot of that work around the planning and approvals and compliance. If you know your pathway forward at the start and you know the certainty and you know the risks, then you're in a good place to move forward without then suddenly realizing you're in trouble. And there have been instances of things like new mines opening up, or proposed mines opening up, or projects being proposed where they've gotten to the point where they're about to go operational, and the regulators come back to them and said, no, you're not compliant, or we're not going to license you to do this because you haven't met these conditions. So it's a massive risk, and I would say get it right up front, get it right at the start, but keep on evaluating it as the project moves along. If you come with a design change, you have to bring in all your stakeholders for that design change and just check that it hasn't affected one of your planning and approvals or compliance pathways.
In most instances, do you find that with the information that's sort of available at that desktop level is pretty much giving you a pretty good level of certainty before you go out and do additional baseline monitoring, or is it the other way around? Most
Yeah,
of the time, we've got to do.
honestly, I would say it's the other way around. I've rarely seen a project been able to suffice with just desktop study information. Going out to the field is a critical element for an environmental management and approvals program. If you don't have that field element, there are things that you can't recognize through a desktop study that you'll recognize on the ground, and it will become obvious that you've got a data gap or a key issue that you'll need to address.
All right. Shall I move to the next slide?
Lovely. So looking at management plans in further detail, there are a few common documents or components that we would consider in a dewatering and discharge scheme. The first and most obvious is deciding on your dewatering method and design, which I'll talk to a little bit later on. You may decide, for example, that a sump pump is sufficient for the base of an excavation because the footprint or the depth is quite small and the formation is relatively well consolidated, so there's no risk of it slumping in. For larger projects or high permeability units, it might be more beneficial for you to dewater the local extent prior to and during excavation using abstraction dewatering boards, or adopt an exclusionary method such as cut-off wall or a cofferdam. Once you've decided on your approach, you can actually start working on the other components now, including deciding on your monitoring program, deciding on your surface and groundwater investigations and monitoring, and deciding on a discharge and reuse plan and a water treatment strategy, because you'll have a better handle on how you're actually going to manage the water. And then these can all be integrated into an overarching environmental management plan, or more often than not, a sub-plan, which is your water management plan.
From your experience, like we had Greg Hoxley on the other day, did a webinar, and he mentioned that the level of rigor required for the groundwater side of things before getting approvals is going up. Does that concur with yourself? You're finding they're needing more and more rigor, or?
Oh my God, they've always needed a great deal of rigor. And I would say they're getting more scrutiny now than anything else. I've seen it a lot with licensing of discharges, and I've also seen it with taking of water for dewatering. Part of that is born out of the evolving guidelines and understanding of groundwater systems, and part of that has arisen out of learning from mistakes made or bad practices. Identifying the need for stricter rules around the approach, and even just consistency around the approach. One of the most infuriating things as a consultant is when there's a lack of a guideline and people are doing all sorts of things in different ways that can cause risk.
Makes sense.
So moving on from management plans and onto the fun world of approval and licensing. Once you've got a draft of your environmental management plan, it's time to submit that to the regulatory authorities and ideally cross your fingers and hope you've done all your homework, because they will know if you haven't. They'll review your documentation, check if it's all in order, and provide you with the relevant permits to proceed. And it's not always a matter of once and done with this process. You may find out that they've got some hang-ups that you need to address, and you have to go back to the drawing board with your water management strategy. For access and take, your water management catchment, for example, might not have sufficient available volume for you to extract water, and you might have to go and consider something like a managed aquifer recharge scheme or a closed loop system for your dewatering project so as to not impact on that aquifer. Or you might have to go to market and buy some allocations and hope that there are enough available for your scheme to go ahead. For discharges to receiving waterways, you might find that the EPA are not comfortable with the level of risk to the environment caused by the release of your water. And you may need to further explore your water management options, such as maybe irrigation schemes, transferring that water to other users who could use that water, even at its level of quality, or a trade waste agreement for discharge to sewer. And it's important to note here, for discharges to sewer especially, that many of the public water treatment plants in Australia are either at or over capacity under their normal operating conditions, especially so in the regions. So discharges to sewer generally have limited success unless the volume is very low. And even then, there's discharge limits. I would say limits on, water quality limits around discharge to sewer, which you might not be able to achieve for your site. So once you've got your permit, fingers crossed you've got it and everything's kind of your way, you'll need to expand on your environmental monitoring program. It's often a condition of these licenses that you have a robust monitoring program in place, and then you continue to monitor. You might be required to monitor and report, for example, on your abstraction rates for compliance with the water access license. You might be required to monitor and report on water levels and drawdown, not only to assess potential impacts to aquifers under the aquifer interference policy in New South Wales, but for potential risks from subsidence, which is a particular concern for dewatering projects in urban areas where subsidence could cause major issues to the foundations of buildings and linear infrastructure. So water quality monitoring at your licensed discharge point will be used to inform the EPA on your compliance with your discharge limits, and they may choose to set a volume limit to balance your potential risk to the environment, which would require you as well to conduct flow monitoring. It's important that your monitoring methods are undertaken in accordance with the approved methods, not something you've made up yourself, as a failure to do so could result in a non-compliance and penalties, and the penalties are often quite steep. You could be looking at $60,000 for something you could have invested in and maybe spent $5,000. So if you skimp, you can sometimes get punished for it. Typically, I would say you're required to adopt at least the Australian standards, but there are state level guidelines and standards might also be required. For example, the New South Wales EPA have their own approved methods for the sampling and analysis of water pollutants in New South Wales.
That side of things, just in the context of emerging contaminants and things like PFAS, that sort of plays against real-time monitoring at the moment, right? So do people have to do a lot of batch testing, or do they sort of do a bit of a baseline and then say, okay, look, these parameters or these particular contaminants aren't present, and then move towards a sort of refined suite of parameters that they test for?
Yeah, that's typically the case. You may not need to. You'll always have to batch test until they come up with real-time sensors for specific contaminants. And some of the newer sensors that I know about are sensors for ammonia and nitrate, for example. But toxicants and PFAS, it's sending these samples off to a lab to get tested down to the levels of reporting that they need to be tested for, and in accordance with NADA accreditation. So you may only need to do that. And one thing it's good to explore with regulatory authorities and the EPA is to say, maybe we'll do this monitoring program on a weekly basis, and we'll do it for 6 months, and we'll establish, again, talking about statistics, samples and populations, we'll establish what that statistical variation is, and we'll set ourselves, we'll give you an example of what we're finding over time as average and reasonable worst case conditions and best case conditions, and you can push to base your licensing off that variability, provided, again, coming back to it, that you're taking measures to avoid that risk. But there's definitely, it's not sustainable economically or even practical to continue batch monitoring on a weekly basis, for example, for a water treatment plant, for the whole of its operation, which might be several years, it might be tens of years, might be decades.
All right, shall I move to the next slide?
Awesome. So now we've rounded off our discussion on planning and approvals and compliance. We'll take a shallow dive, and hopefully smash my head, into dewatering and wastewater management techniques. What it's important to note here for any dewatering and discharge management system is that any effective system is a combination of both critical engineering decisions and critical management decisions, which need to be drawn out through collaborative discussions between management and engineering on what the solution is going to be. In my experience, systems will often fail to meet their objectives when there's limited dialogue between the operational and the environmental managers, and where the engineers in charge of the design process haven't had a chance to actually liaise with either of those parties and come up with suitable methods to risk out key risks. So managers, for example, might require that processed water streams are treated and recycled through a processed water system rather than being discharged. The engineers can then respond with the necessary engineering methods, such as bringing in a water treatment plant to support this management decision. In the converse, an engineering team might require dewatering at a certain rate to facilitate the excavation of a pit, and the management and environmental teams will be required to determine appropriate solutions for the reuse and disposal of that water in accordance with your license conditions or with your environmental management plan. So for dewatering projects, the common techniques I see are sump pumping, which is quite simple and cost-effective for shallow excavations, or any excavations in consolidated formations where you don't have to worry about the risk of sumping. Well point systems and deep well systems are also used with straw water from around the excavation, and are more advantageous for permeable aquifers where the stable excavation slopes are required. So you need to stop those slopes from slumping. Horizontal drains are used quite often in open pit mining and in slope stabilization projects. They can be very effective and low cost if gravity drainage can be achieved. If not, then you're potentially looking at some quite expensive pumping. By and large, I would say the best method is an exclusion method where you put in a cutoff wall, grouting, ground freezing, or cofferdams. And these methods have been widely used in Sydney's major tunneling projects in recent years for things like the station box excavations and the shafts. So once you've dewatered, to move water along, you might want to consider interconnected pumps and pipelines to transport the water at the rates you need to maintain dry excavation. That means sizing those pits and pumps according to your expected inflow rates and the need to move that water. Where gravity drainage is enough, you might just decide that you're going to opt for channels and drains to move water downstream and away from the area of active excavation. For example, in an inclined tunnel where you're going back up again, you can just use gravity drainage rather than having to pump it. So once you've taken that water, you've dewatered it, and then you've moved it along through your conveyance, it's got to go somewhere. And often than not, a treatment technology is needed. And so these treatment technologies, they're highly varied. They're specific. They often need to be specific to both the volume of water and the water quality, and the pollutants that have to be removed. Correction of pH and total suspended solids. This can be achieved with relatively simple dosing system, let's say of sediment basins with flocculant and acid or caustic to correct pH. Or if needed, this can be done through a clarifier and a pH dosing system, which is more a mechanical water treatment plant. So further polishing of sustained, if you want to go even a step further and really polish the water, you can use things like sand media filters to really get the TSS down. If you're dealing with more contaminants, you might need more advanced treatment systems, or you may decide constructed wetland is the approach. One of the limitations of a wetland is that it takes time to establish before effective pollutant removal can be achieved. So as a result, it's more suitable for longer term operational projects than it would be for a construction project. Also, you have to consider location. You know, if your site is near an airport, you can't put a wetland in because the birds will fly into the planes and you'll have all sorts of casualties on your hands. So don't put a wetland near an airport. So the water treatment plants, they can remove contaminants through the use of, you know, either standard or both standard and innovative treatment technologies. Some of the standard treatment technologies that I've seen have been granular activated carbon, green sand media filters, breakpoint chlorination system, and even zeolite filters. But some of the newer and more innovative technologies, you might be looking at ion exchange resins, electrochemical removal, or even reverse osmosis. But this technology does have a few limitations. Firstly is the generation of a waste brine, which for some RO plants can be as high as 40% of the overall liquid volume, which, you know, if you're dealing with even a megaliter per day, you've got, you know, 500,000 liters of concentrated waste brine you've got to dispose of somewhere. And there's also a need to recondition that water after treatment because it's been stripped quite aggressively of all its water quality properties, even the major ions that are essential to water quality in aquatic ecosystems. So if you discharge that water, sometimes it's so pure it can be even detrimental to aquatic ecosystems.
So when you're choosing your treatment system, and I know you were talking about re-injection before we started, there's obviously a fair bit of approvals process to go through there to work out the sensitivity of the receiving environment, even the aquifer that you might be re-injecting into. If you make no change to the water and you re-inject it, you've still got to do all that testing, don't you?
Yeah, you still need to do the testing to demonstrate that there's been no impact to water quality. So typically, for a re-injection system, you'd be testing that both through the loop and then down gradient in that aquifer. And the reason being that, you know, those changes, maybe even in flow rate, can sometimes mobilize metals that you might not be aware of, or, you know, maybe your injection system or your, you know, dewatering system has exposed some acid sulfate soil, for example, and then you've mobilized, you know, you've acidified the groundwater and mobilized heavy metals.
Right.
Yeah. The test, though, the ultimate test, I think, is well, in New South Wales anyway, is you refer to the aquifer interference policy and go from there. Cool. Well, look, first case study. So this one is very close to my heart because I've been involved in all of the tunneling packages in some way as a water quality consultant. It's the Sydney Metro West tunneling packages. So the Sydney Metro West is an ongoing project which involves construction of 24 kilometres of twin tunnels, creating a new underground railway to double the rail capacity between Greater Parramatta and the Sydney Central Business District. Tunneling work for Sydney Metro is divided into three principal packages. That is the Western Tunneling Package, the Central Tunneling Package, and the Eastern Tunneling Package, each of which has been awarded to a specialised joint venture or a consortium. Each package contractor has had specific responsibilities for implementing water management measures within their designated section of the alignment. And the management of water resources during the construction of the Sydney Metro Western tunneling packages is governed by a comprehensive and overarching framework of environmental approvals, project-wide standards, and contractor-specific plans. This overarching framework ensures that the potential impacts on water quality and water resource are systematically addressed, mitigated, and monitored throughout the project in a consistent manner, despite there being three separate contractors working on three separate sections. So the Western Tunneling Package, this extends approximately 9 kilometres and involves the delivery of the twin metro tunnels between Westmead and Sydney Olympic Park. It also includes excavation for 2 new metro stations, a stabilising and maintenance facility at Clyde, and a precast facility at Eastern Creek. The central tunneling package spans 11 kilometers, and that's between the bays and Sydney Olympic Park. It also involves the excavation of 5 new metro stations. And then we've got the Eastern Tunneling Package, which is the smallest of the packages, but by no means the least complex. It only covers 3.5 kilometers of tunnel around the bays and Hunter Street, but includes the excavation of the Pyrmont and Hunter Street metro stations and a turnback cavern. And it's one of the more complicated areas, I'll say, because there's a much greater risk of saline, with it being quite close to the waterway here, much greater risks of saline intrusion. And so that also needs to be managed along with standard water quality management measures. So the excavation of these deep tunnels and station boxes has interacted with some quite complex groundwater systems and has made groundwater control and management a critical aspect of the Sydney Metro West project. The effective management of groundwater has been central to ensuring structural stability of the project in this urban environment, and also on minimizing environmental impacts to receiving waterways. Managing groundwater inflow into the excavations has been quite a challenge, not only due to the variable permeability of the formations and predicting groundwater inflows, but also due to the presence of contaminated groundwater in some urbanized and historically industrial areas, which have had a long legacy of significant environmental contamination, and they've needed careful treatment and management to avoid environmental impacts. And there's a few of these sites that are legacy landfill sites or legacy industrial sites, which, for example, have excessive levels of hexavalent chromium or, other major contaminants and TRHs and PAHs, and there's been electroplating. So these are some really nasty disturbed sites where, you've got a volume of water coming in, and it's not a small volume, and you've also got very poor water quality. So the primary strategic objective throughout this project has been to reduce that volume of water so that to minimize that environmental impact, rather than have to pump a lot of water and treat a lot of water. It's reduce as much water as you can coming in. And that was even, I think, set at the ministerial level, at the planning level, to limit the inflow rate into the tunnels to, I think it was 1 liter per second. A lot of these tunnels now, they're constructed using tunnel boring machines with earth pressure balance or slurry modes and progressive tunnel lining, so that no water is coming in during tunneling. It's only just processed water for the most part, and maybe a trickle of water that it gets its way past the EPB. Then we've got the use of diaphragm walls, secant piles, waterproof slabs and station boxes, and that's also contributing to minimizing that water volume. After that, all the water that is coming in is being treated with some of the most advanced water treatment plants in Australia for the removal of contaminants and excess water. This includes ion exchange. There's a reverse osmosis plant. There is, granular activated carbon, as we discussed before, breakpoint chlorination, specific resins removing specific contaminants. Rather than simple, DAPs, there's clarifiers as well with sludge removal systems. So very advanced technology, millions and millions of dollars, very expensive pieces of kit. For the Western tunneling package, water's moved through the tunnel using temporary sumps, and it's pumped to the surface through pipelines up to the water treatment plant, where flow meters are installed within the pumping and conveyance system to accurately measure the volume of flow being pumped to the water treatment plants. This is useful in not only the operation of the water treatment plant, but the design of the water treatment plant is knowing how much water there's going to be coming into it, because the water treatment plant's only going to be able to treat a certain rate of water. Maybe it's 5 liters per second, maybe it's 15 liters per second. And if you go beyond that, there'll be a need to divert the water, or the efficiency of the water treatment plant will drop away, and you won't be able to treat contaminants to the levels that are needed. So to try and manage water as much as possible, to try and reduce that water from going through the water treatment plant, applications for reuse of water in the project mounds have been robustly explored, including using it for dust suppression, using it for conditioning and compaction of fill materials, using it for equipment and vehicle washdowns, and using it even for concrete production. And the sustainable use has been central to these construction activities. I would say that's been the central theme. Environmental protection licenses have been central to operation of the project as well. And in particular, the EPLs have requirements on your concentration limits, requirements on monitoring and recording, on reporting conditions, and most importantly, for these water treatment plants is the incorporation of further pollution reduction studies to continually optimize the water treatment plants, to continue to explore trying to reduce contaminant levels before they're being discharged. And that might be, progressively through additions to the water treatment plant, or by, adjusting your dosing rates to achieve better removal of TSS. So these EPLs more often than not, they're not static documents. They'll set conditions, and you'll have to achieve these conditions along the way. Once you've achieved them, you'll step through to the next phase, and eventually, for construction anyway, you'll close out the project and transfer the license over to your operational phase.
All right, shall I move to the next case study?
Sure. So our second case study concerns Wastewater Ash Dam, which is an area in New South Wales. The ash dam has a long industrial legacy involving coal ash storage and involving environmental controls as the site's expanded. The site's now undergoing rehabilitation. So towards the end of its operational life, the Wastewater site comprised several major infrastructure components, including the Kerosene Vale Ash Dam, used for wet ash disposal between the 1960s and 1980s. Sawyer's Swamp Creek Ash Dam, Sawyer's Swamp Creek Ash Dam, which operated between 1980 and 2003. And the Kerosene Vale Ash Repository, where dry ash was placed from 2003 until the Wastewater Power Station ceased operations in 2014. And the K-bar was built upon the top of the K-bad. So it's dry ash sitting on top of wet ash. The objective of the water management at the Wastewater site was to contain seepage from the SCAD, the Sawyer's Swamp Creek Ash Dam, which is that area on the right-hand side containing all the water, and contain it from the K-bad and K-bar within the site boundary, and to limit potential impacts to the off-site receptors, which included Sawyer's Swamp Creek, while also diverting clean water around the site so to not overwhelm that water management system. The seepage control was achieved through a network of subsurface drainage and pump back systems where water was intercepted and collected on site at downstream locations and then pumped back up to the ash dam. The KVAD, which was buried beneath the K-bar, generated leachate from rainfall infiltration, and residual pore water was the source of that leachate. The tow drains installed at the base of the ash dam were used, they were installed to collect the leachate before it had the opportunity to migrate laterally into the surrounding environment. The K-bar generated its leachate from rainfall infiltration, most of which would accumulate in the ash mass as pore water. So horizontal collector drains in that ash mass would then divert water to connect the connected collection basins.
They retrospectively installed, or
they were installed during emplacement of the ash dam. Yeah, some of them later on were installed as it was found that the measures weren't effective enough, but for the most part they were built as they went along. So all the seepage that was collected from the K-bar and the KVAD was directed to a pond called Lidsdale Cut Pond, which you'll see on the far left-hand side in the yellow dots. Originally, this was a mining void, and it was converted, to a seepage collection point for the entire system. From that point, the water was recirculated back to the SCAD and the dirty water pond by a return water canal, which you'll see at the bottom of the image, along with any gravity drainage that was collected and pumped back. All of the pump back systems, they adopted float switches and programmable logic controllers to ensure that the water was being transferred under a timely manner, and it wasn't overwhelming the system. So there was that active monitoring going on throughout this operation to make sure there weren't overflows occurring and offsite seepage to the environment. The ash dam itself, it was managed through a V-notch weir and a pump back system at the base of the SCAD. The system intercepted water through a series of engineered drains and outlets and returned it to the ash dam pond, ensuring that any of the uncontrolled flow was retained within the site within that managed closed hydrological loop. For the groundwater component, a network of monitoring bores were positioned throughout the site to provide that spatial and temporal data on groundwater flow and quality trends. And these help to detect any vertical or lateral migration of leachate from the KVAD, KVAR, or SCAD. And look, although the best management practices were adopted, maintaining a closed hydrological loop for a site, any site this large, is quite a challenge, especially when you've got large areas open to rainfall and high permeability of formations all around the site. So even the KVAR and the KVAD, it was an uncapped ash dam. Which means there's a lot of rainfall passing through that. It's getting into the groundwater potentially, and it's certainly seeping off the overland routes. So as a result, and towards the rehabilitation side of things, containment of the leachate was a key measure to be installed, and some of the future improvements that were proposed when I walked away from this project were included capping of the KVAD and the KVAR with a low permeability capping layer, and construction of a passive wetland treatment system in the Lidsdale Cut Pond, which until then was just a pond. Groundwater balance and modeling works identified that the capping would reduce seepage volumes by between 30 and 80% within 1 to 12 years, depending on the cap permeability, while construction of a passive wetland treatment system could reduce the contaminant loads in the excess leachate by up to 80%. So these two combined management measures would help to reduce the potential risk to downgradient groundwater and surface water quality throughout that closure and rehabilitation stage of the site. Excellent. So our third and final case study, another one quite close to my heart, looks at WestConnex M8, formerly the M5, which is a significant component of Sydney's motorway network and a recent infrastructure upgrades. The first stage of M8 became operational in 2020, and it comprised 9 kilometers of twin road tunnel between Kingsgrove and St. Peters. The second and third stages were then completed in 2023 and added more tunnel sections between St. Peters and Roselle Interchange, ultimately extending the total length of the underground tunnel network to nearly 22 kilometers when you consider the M4-M8 link. So many of Sydney's road tunnels, including the M8, are considered wet tunnels, where groundwater is allowed to naturally seep through the concrete lining. A plastic membrane is installed behind the shotcrete to direct the water down into drainage systems located at the side of the tunnel, which collect in these drains they're known as Jersey curbs. Water then flows from the lowest points to the lowest points in the tunnel, where it's collected in a sump. And from these sumps, the water is pumped to surface for whatever appropriate management measure is adopted. And a critical and unique element of the M8 operational water management system is their operational water treatment plant. The facility has been designed to treat a substantial volume of groundwater on a continuous and a perpetual basis to ensure compliance with some stringent environmental regulations before the water can be discharged to the local receiving environment, which is the Cooks River. And some of the challenges of this is that this area, the tunnel passes through and it's built around some quite significant historic legacy landfill sites, which can significantly degrade water quality coming into the tunnel. So the Arncliffe water treatment plant, located in this image here, that's been designed to treat and discharge around 2 megaliters every day of groundwater every single day. And the design capacity is a critical parameter influencing the plant's scale and operational strategy. And those volumes, they're also quite highly variable, and as groundwater responds to rainfall. So effective water management and mitigation of environmental impacts at the M8 water treatment plant is managed through a combination of flow balancing and by advanced water treatment technologies. The balance tank plays a crucial role in the efficiency and stability of the treatment process, and it's designed to provide a constant and regulated flow of water to the subsequent treatment stages, without flow equalization, the variations in groundwater inflow rates could be directly transmitted to sensitive downstream units, leading to reduced efficiency of the water treatment plant, to process inefficiency, and inconsistent effluent water quality. So managing the flow of water with that balanced tank is absolutely critical. And it's critical for many of the Sydney's road projects. Arncliffe then goes a step further. It adopts a multi-stage treatment system, which combines the physical and chemical treatment processes to remove contaminants from the groundwater, and then discharge actually in a critical next step to a tidal storage basin, which is located adjacent to the water treatment plant. So this tidal storage basin is used to detain the water, treated water downstream of the treatment plant as a final holding point, and allow a controlled release of the effluent only on the outgoing tide in the Cooks River. And the practice of discharging treated effluent specifically during the outgoing tide is a deliberate one, and it's an environmentally considerate one aimed at preventing the localized buildup of contaminants near the discharge point in the Cooks River. And that is, if you're discharging consistently during ebb and flood tides, what's going to happen is that discharge plume is going to move back and forward and accumulate in that river until it builds up to a critical point where it's overwhelming the system. So by discharging only on the outgoing tide, it goes out as plug flow, and you might get a percentage component of return flow, but whatever that is then washed out in the next ebb flow event. So it prevents that accumulation, and then every now and again you get a big rainfall event and it'll flush the whole system. So it's good. It's a good method if you've got the space to put in a tidal storage basin if you're dealing with a lower estuary. So the entire water treatment plant, including the discharge system, is operated and monitored from an external control room. And this centralized control system provides the operators with this full functionality to oversee the plant's performance, to monitor the water quality at various stages within the treatment process, and to manage plant alarms and operational status in real time. If there is a non-compliance issue, for example, through one of the sensors, they can stop that water from discharging and recycle it through the plant if they need to. Often, sometimes if you don't have that buffering capacity, such as with this tidal storage basin, you may not have that ability to then cycle the water back through the water treatment plant. So that continuous monitoring.
David, yeah. So in that scenario of discharging on an outgoing tide, is there actually monitoring within that, I guess, mixing zone that's done to confirm that it is actually working?
Absolutely, yeah. So part of, and this is built into the EPL, part of the management strategy is to conduct regular water monitoring in that receiving waterway at the discharge point, up gradient of the discharge point, down gradient of the discharge point, and in the adjacent waterway in Alexandra Canal. And that all has to occur for the upstream point prior to discharge and the downstream point prior to discharge, and then again during discharge or slightly after discharge at the discharge point, and then up and downstream again. And that provides a comparative check of baseline against disturbed condition. And that's an ongoing long-term monitoring program, which the collection of data, allows you to look at trends over time and assess whether or not over that time there has been any material change to the receiving environment.
All right, shall I move to the questions, David? We're sort of a little bit over time.
Sure, absolutely, yeah.
Thanks very much for that. That was excellent. All right, a lot of early bird questions. First one up, can saturated spoil be stripped to mine sterilised coal? That's a bit of a curveball, right off the...
Yeah, interesting question. The answer, I think, is yes, if it's economically viable and safe. Considering material handling and potential instability is something you'd need to think about. The question there to ask would be, is it cohesive enough to be moved without the risk of it slumping? And is the cost of moving and storing that spoil suitably weighed against the value of the underlying coal?
Next question, how do you manage salinity from rising water tables via dewatering?
Yeah, so it's a tricky question, but it's one that I've had a little bit of experience with from a few sites, and particularly from the lower Burdekin Basin. One of the options is to lower the groundwater table with pumping bores, and where possible, discharge that water out into the open ocean. This will help to mitigate the risk of the rising water tables affecting soil salinity and surface soils and crops, for example. And if you're dealing with an agricultural landscape such as the Lower Burdekin, you could look at encouraging more, maybe as an alternative, you could look at encouraging more efficient irrigation practices to reduce groundwater recharge through those artificial means. And I would say, as a general rule for maybe any project where you've got an open groundwater system, reducing the recharge rates can work to help reduce the rate of rising groundwater tables and rising salinity that goes with that.
Next question, how to optimize polymer additions to slurry feed to a decanter centrifuge?
Yeah, look, I mean, you're probably best talking to a water treatment plant engineer in this case. But from my experience with most any of these systems, when it comes to optimizing, you're starting off, but before you've actually, commissioned your water treatment plant, you're starting off with your jar testing. Then once you're, at the commissioning stage in the water treatment plant, you're moving on to trials during that commissioning phase to see what kind of dosing rates and sort of use of the centrifuge you need. And then you kind of move on to active monitoring during operational phase using maybe real-time sensors and using those to control dosing and torque in the centrifuge.
All right, next question. What is the best way to deal with sediment-laden water?
Yeah, I mean, look, the answer to this, it depends on your application. If you're dealing with a sediment basin, for example, you might opt to use alum hydroxide as an effective flocculant and coagulant. If, however, you're dealing with a regulatory authority and they're concerned with the toxicity of aluminium when the water is released, then you might have to opt for a more environmentally friendly but less effective alternative, such as gypsum or calcium carbonate. In a water treatment plant, your options are more varied. You can use clarification, dissolved air filtration, sand media filters. If you really need to polish your TSS, then these are the best options for removing sediment-laden water.
All right, next one. How can water balance for landfill sites inform leachate management practices?
Well, look, a water balance will quantify all the water inputs for a landfill. It's a little more, and that's typically it's all coming from your rainfall. It's a little more complicated to predict the volume of leachate that's generated solely from internal moisture and decomposition of your waste. But once you have derived that value, I would say you then need to incorporate it into your water balance to help you manage your landfill site. That way, you'll have a grasp on landfill leachate volumes generated from the material itself, along with potentially any rainfall irrigation, rainfall infiltration that's occurring.
Yeah, I think it's worth adding that knowing your estimates of evaporation from your leachate ponds is an important part of that water balance. And often you've got groundwater inflows from unlined systems that need to be taken into account as well. All right, next dot point, water release compliance monitoring. Well, we touched on that, that's for sure.
I'm not too sure what the question was, but it's an important topic. The EPA, the regulatory authority, you might, in some instances, you might only need to engage with the local council. Yeah, there's ways of doing it. You just need to make sure you're compliant.
Maybe the question is, who are they going to get? Who needs to sign off on that?
Yeah, so if you're the license holder, ultimately you're responsible for maintaining compliance with your license. You may choose to engage a consultant to do that and provide reports to you, which you then submit, but ultimately it's you.
All right, next question. How do you deal with water balance in I'm presuming it's high plasticity clays and heavy fraction hydrocarbons in confined water-bearing layers? There you go.
Well, I think two of the issues there are the low permeability of the clay and the viscosity of the hydrocarbons, if I'm thinking about this right. Managing the water balance, I think, would require careful control of pressure, and you could look at hydrocarbon recovery techniques such as using a steam or solvent injection, coupled with a containment strategy to prevent the migration of hydrocarbons when you're dewatering those clays.
Good answer, David. Next one, implications of dewatering on acid sulfate soils.
Yeah, nasty stuff. So those acid sulfate soils, when when you're dewatering and exposing them to air, they're going to produce that sulfuric acid, which can, the acidic drainage, it's harmful to the aquatic ecosystems and the built infrastructure. It can corrode that built infrastructure, having low pH. But it can also result in the release of heavy metals such as aluminium, iron, and arsenic from soil formations into the water, causing toxicity. So I would say the implications there are, they're not only the pH, the low pH implications, but they're also these toxic metals that are being released by that process.
Best approach to manage discharge of groundwater with elevated heavy metals for small excavations where treatment will be costly?
Yeah, look, it's a tricky question because, well, for a few things, your treatment depends on which heavy metals are present, and often while one treatment, you might decide one treatment works for this metal, it might not work for the other. So you end up with dosing multiple things into the ground to try and treat it, but some of the options you could explore might be in situ treatment, or you might choose to find a way to immobilize or degrade the contaminants in situ. If you've got for small excavations, I would say where maybe you don't have a lot of water, you might be better off considering an on-site containment tank, and then from there off-site disposal to a licensed facility. You could, it's probably harder to consider something like closed loop reinjection to groundwater, but if that water is already contaminated, because even, we touched on this before, Richard, but where groundwater is already contaminated, it's quite well frowned upon about reinjecting that water, unless you really have a reason to do that. The other option, which it's maybe arguably it could be environmentally less sustainable, is shandying the water. So you take that water and you dilute it with some potable water or some fresh water you've got from another area, mix it all together, and then you can discharge that, and it will be, it could be potentially within sustainable limits if your freshwater source is clean enough.
Okay, next question. In your opinion, what is the best analytical method to calculate groundwater flow extraction? We use cone of depression calculator.
Yeah, so it depends on your method. It depends, on the type of aquifer you're dewatering and the specific dewatering method you're adopting. There's a number of analytical solutions available to explore. What I'd recommend from my experience, if you're looking at online tools and what's in the public domain, is you can check out Halford Hydrology's resources, or you can check out some of the work that Kik Hemker has done on putting together analytical models for excavation dewatering and dewatering bores.
Next one. Where do sites most often go wrong with water balance?
Yeah, so we touched on this, I think, earlier in the presentation, but in my experience, that the most common and widespread issue is a failure to gather your local site-specific data on the water balance conditions, and instead rely on things like regional models or empirical estimates to fill in the gaps. This, more often than not, is going to lead to inaccurate estimates on your climate variables such as your rainfall rates and your evaporation rates, and it can lead to a poor understanding of the local hydrology. So as we touched on before, the old saying is you put garbage in, you get garbage out, and if you start with the wrong information, you're going to get the wrong answer. So I would encourage you to spend a bit of money up front on collecting your local data to inform that water balance before you spend money on water balances and getting it wrong and having to go back to the start.
Right, next one's a landfill question. At mixed recycling landfill sites, how do we define wastewater versus clean water, especially runoff from sorting C&D waste?
Yeah, so I mean, this is common to most sites, even construction sites. Wastewater is generally any water that's come into contact with waste materials or an active waste processing area. So runoff from sorting C&D waste, for example, would be considered wastewater because it can pick up contaminants like dust, debris, chemicals, and leachate from residual waste that's in the C&D stream. So leachate collected from landfill cells is also, clearly wastewater. Any water used in washing equipment or suppressing dust in active areas would fall into the wastewater category. Everything going through your site in your disturbed area is going to be a wastewater stream. the contrary to that is any water that's diverted around your site or around these operational areas that can be classified as clean water.
Have you investigated biochar for filtration of water from the dewatering process?
Look, I haven't personally. I understand that it has been investigated through a number of research papers. My experience has been that the go-to at the moment is granular activated carbon, and I think the reason for that is because the GAC has it offers higher porosity and a higher capacity to absorb contaminants. It is potentially in a lot of instances higher cost, but there's better control on the quality of that GAC, leading to more consistent outcomes.
All right, we're on to the Q&A questions. Happy to keep going, Dave. This is excellent.
Sure.
Hez Murray's got a question. There seems to be a preference in the international community towards fee flow over mod flow, while Australia seems more mod flow orientated. Any thoughts or comments on this with regard to mine water balances, with dewatering being the primary component?
I would say that answer, it comes down to what is relevant and what is considered standard best practice for at a national level and at a state level. So while the preference, some people might decide they're going to adopt free flow and that it's a better model, in the grand scheme of things, what really matters is what the state regulatory authorities and the national regulatory authorities, if that's relevant, will accept. They both have their pros and cons, their benefits and limitations, but what matters is compliance with standards.
So there are those Australian standards for modelling. Is that what you're referring to?
Yeah, there are those standards, and then there's also per project, there will be guidance from the regulator or the scientific body on what's acceptable practice. They may decide that fee flow is okay. I would say, early engagement and setting the ground rules about how you're going to model with the regulators and with those authorities is going to be key. At the end of the day, that standardization is entirely down. It's something that's still in the air. So in time, that'll be fixed, I think.
Do you think the regulators have the depth of knowledge to be making the call on these things?
I think, many of them do. Many have very good in-house technical teams. So they'll have their regulatory teams and their officers who do the day-to-day stuff, and then they'll have the technical teams who sit in the back room, in the dark back rooms in the basement, doing all the nitty-gritty work. Certainly in Queensland, there's a strong technical team, and there's the same in New South Wales, from my experience. It's just whether or not they have sufficient time to interrogate those models and also come up with suitable, consistent guidelines. And I'd say one of the shortcomings I've seen in New South Wales anyway is an inconsistency in between different policy officers and different regions because of a lack of an overarching framework.
Next questions from Abel Imiraj. The operating scenarios over the life cycle would also inform the parameters and data. I guess it's referring to the life cycle of a infrastructure project.
Yep. Yeah, that's right. That's right. So talking again about water balance, you're doing it at the start of the project to set your water management strategy up, and you're doing it, you're continually doing it throughout the operation of that project as you find, your variables change, over time, or new maybe there's new process water, inputs and outputs. So, you're constantly evaluating and reevaluating that water balance and integrating new components, which, it does help to build at the start of this, a framework, an adaptive framework, so that you can adaptively manage your water balance components. If you build something that's fixed and rigid, and you get locked into, then you can have some real problems trying to adapt to new measures.
James Stewart from Always Carbon. Very interesting session. Thank you. Curious, given climate change introducing water supply uncertainty, are you seeing increased interest in closed loop systems?
Well, I encourage closed loop systems as much as I can, and I think it's important that we try and move towards, for a lot of sites, we try and move towards a zero liquid discharge operating conditions, during construction and during operation of projects, because as we touched upon in the early history, discharges of contaminants into water can have, serious environmental impacts to, ecology and the beneficial uses of those waterways. And, oftentimes there are opportunities to achieve that zero liquid discharge by things like re-injection, by things like, irrigation, or even, closed loop systems with storages and evaporation. The problem that I find is there's a lack of regulatory guidance and regulatory involvement in, enabling those approaches with individual sites. It's very piecemeal, case by case basis, and I think a lot more work could be done towards improving that.
Next question, when you assess potential impact of a dewatering system, do you adopt generic or site-specific water quality levels?
So is this for discharge, or is this for?
I think so.
I guess it would be discharge. Yeah. Look, the default guideline values are the starting point always. The target will always be that you have to meet those criteria, and they're enforced quite rigorously by a lot of the environment agencies, to make sure there's no deleterious impact to waterways. So that's the starting point. You can move into deriving site-specific trigger values. One of the complicating factors with that is SSTVs under the ANZAC framework, are actually based on local reference site conditions, but from pristine waterways. So you'll end up trying to set an SSTV, and you'll find that, your SSTV is actually lower than your ANZAC guideline value, because, the only waterway that's near enough is so clean that you can't achieve that guideline value. In fact, what's more appropriate here is not per an SSTV, but a pollutant limit that reflects the potential risk to the waterway based on the assimilative capacity of that waterway. And that's done by demonstrating through a water discharge impact assessment that there is no significant impact to that waterway. Let's say, for example, you're discharging, you've got maybe cadmium at, marginally higher concentrations than the ANZG guideline values, and you want to discharge it into a very open, broad waterway. You do a dilution model, or you do a discharge model, such as, you could use a simple analytical approach, or you could use something like Cormix. If you can demonstrate that there's no material harm to that waterway, you can get away with, and you can get approved what is a regulatory mixing zone. And in that mixing zone, you don't have to achieve the water quality guideline value, but when you get to the edge of that mixing zone, the water has to have returned to ambient conditions or below, well, really below the ANZAC DGV.
If the ambient water quality levels are higher than those DGV values, like, what's the point?
Yeah, that's touched on a topic there. It's a real problem. We'll often get told that about an environmental value isn't being met for a waterway, and so there's no way to discharge that environment without making the condition worse and continue to exceed that default guideline value. It's quite typical. A lot of the agencies will adopt 95% species protection, and for bioaccumulating toxicants, they'll adopt 99% species protection as the the environmental value, the target for that waterway. Even in some of these really degraded systems, that's always going to remain the target to maintain and improve water quality. So where that's already disturbed, you're going to have a much harder time trying to justify a discharge as the catchment's already effective. And what the EPA are trying to do, and rightly so, is to mitigate the cumulative impact from multiple licenses onto a system. And they're trying to bring down that level of contamination. So, you can go as far as you can. Ideally, the water is already in a good condition, and your discharge won't adversely affect it beyond, slight change within that mixing zone. But for an already degraded system, it's very hard to justify a release.
All right, next question. In your experience, do the EPA seriously consider a change in conditions regarding mass load assessment limit of pollutants rather than mass volume consistent discharge consistent conditions?
Sorry, can you repeat that question?
Sure. In your experience, do the EPA seriously consider a change in conditions regarding mass load assessment limit of pollutants rather than mass over volume consistent discharge conditions? I'm not sure I understand that either.
I'm not sure. Look, mass, maybe a response here is that the parameters that for which mass applies most importantly are the stressor parameters, particularly your nutrients like nitrates, nitrogen, phosphorus, reactive phosphorus, because they're not concentration dependent, they're mass load dependent. And so when you get enough mass passing through a system with maybe a low flushing rate, those particular contaminants will cause an ecosystem response, which for nutrients will be, nuisance algal growth, cyanobacterial, maybe some nuisance growth of weeds as well, macrophytes. So when that happens, it will cause eutrophication of the waterway, which will then cause fish kills. And so mass load becomes much more important than concentration for those nutrients. Whereas for toxicants, you're actually dealing more with your toxicant concentrations in themselves, as they have those acute and chronic risks that can affect the function and the health of aquatic ecology. But it is important to note that a lot of, and this is maybe a failing of the EPA, and this might be what you're touching on, is I wouldn't say failing of the EPA. I would say it's an issue, is that a concentration doesn't necessitate a serious environmental outcome. It is the load, and contaminants should be considered on a loading basis rather than a concentration basis when it comes to licensing functions.
Okay, next question from Mike Jorgensen. For the M8 case study, did the treated groundwater still exceed any guidelines? If so, how was that addressed to obtain approval for discharge to the river?
Yeah, so I mean, I wouldn't say too much about M8, but I will say in general that when you exceed a guideline, and a lot of the tunnels in Sydney will, because they're built under an urban infrastructure, an urban domain, so this will apply to any water treatment plant in any urban setting. Is if you've got a drain tunnel, and your water quality isn't meeting the default guideline values, you will have to get an EPL to discharge that water. When there's no other option, when that water can't go anywhere else and you have to discharge that water, the EPA will recognize that and they'll give you a discharge license. Obviously, you have to demonstrate that you're doing everything you can to improve that water quality, including showing them that you're adopting best available technologies, best practical technologies, and they will audit that. So once you've passed all those milestones, you'll then get an EPL with a higher than the ANZG limit. And that's what the EPLs are there for. They're there to give you limits that are higher than the ANZG guideline values.
Okay, next question. Oh, no, it's just a statement, actually. Darren Brown, he's very happy and says thank you. Rachel Teen, thank you, David. Excellent. Thorough presentation. And have a good weekend. Evan Brooks, how do you see the future for using sewer treatment plants to manage landfill leachate in New South Wales?
Oh, I mean, we did touch on this earlier. The issue with the sewage treatment plants in large areas of Australia, maybe not all, is that they're already over capacity or they're at capacity. And so diverting additional flows into those water treatment plants, it can't physically be done with the volumes available. So it's potentially a good option, but it may not be a practical option given the limited scale of those water treatment plants.
All right, we're getting there. Been great questions. Danda Sapkota says, excellent presentation and really appreciates your time. Next question, what techniques are suggested for reducing BOD in wastewater with elevated TSS, including organic matter, combinations of natural green oxygenating flow with mechanical treatments?
Yeah. So I'll talk to my experience on this. So removing organic matter BOD, TSS, typically you're looking at, for a water treatment plant, you'd be looking at, a clarifier, maybe a DAF, coupled with your media filters, and you're dosing your flocculant coagulant into your clarifier and your pH adjusting to drop out all that organic matter with the TSS, and then you're polishing the TSS further with your media filters. Now, if you've got an operational site and you don't want to spend a lot of money on an expensive water treatment plant, and that site has enough space and a long enough life cycle, you could opt for a constructed wetland, with a series of baffles that will help you to, drop out the TSS and deal with the BOD.
All right. Alison Reynolds says, absolutely agree with how the EPA approach criteria. At times, nutrient concentrations for discharge in the Cooks River is something that comes to mind. So I guess that's more a statement than a question. And Jimmy Whitmore says, love the presentation. Thanks all. So David, well done. That's a epic round of questions you've answered there and a great presentation. So thank you very much for presenting today. It was a brilliant presentation.
Thank you. Thanks for having me, Richard, and thanks to the audience for listening. And I hope you all have a great weekend.
Thanks, David. Bye, everybody.